Memorable. Okay, so we talked about tomography. I gave you the wrong copy. I didn't want to have all the writings inside, but it's done. The main purpose of imaging is that you want to reconstruct an object, the interior of an object, which can be a piece of rock, concrete, the subsurface, and a site, from limited measurements. It would have been nice to have a lot of measurements, but in practice we normally don't have enough measurements. So we always have some sort of a limited measurement, and we want to use that to reconstruct the object. And because of that, you always have to do optimization. So what we are going to talk about is first scanning. In non-destructive evaluation, it's very important to understand the difference between A, B, C, and D scans. And this is something I may ask in the exam. So please pay more careful attention today, because before I kind of casually here and there I told you about this, but I want you to get it as questions. And it's something very useful to know for NDE. And then we talk about one simple way of tomographic reconstruction with some examples. We look at both travel time and attenuation tomography. So in X-ray, we have density reconstruction. In acoustic, we can do travel time reconstruction to get a velocity distribution inside the object, or amplitude reconstruction to get the attenuation distribution within the object. And then we talk about one other reconstruction method, which is called synthetic aperture focusing technique. And at the end, I like us to have a discussion to see which one is, what are the limitations, applications, whatever you understood from it. Okay, I've showed you this many times, but scanning is when we basically repeat the same measurements manually. So you have a grad student most of the time doing the manual test. If you pay attention to these pictures, you see here there are some sorts of grid points, and you basically can move equipment from one point to the other and collect what you have collected in the lab already for one single point, right? However, the state of the art is to use robotic platforms. This is a scanner, and this is my own work when I was in Germany, and you control it with a laptop. So you mount the ultrasonic probe, you program where you want to test, you give all the parameters, then you go and have T, and it's going to do it the way you want it to do. So here we had a piece of a bridge, a real bridge, which was demolished. So we have two test sections, and this robot has a limited area, coverage area, so we had to divide it into two, and then you kind of have to stitch it together. So this you have seen also before. So how it works is you move in this case, it's a pulse echo method. Pulse echo is when you send in the energy and you're receiving on the same side. What was the test you did in the lab? You remember how do we call that kind of test? When you have the transducer and receiver on both sides? Thank you. Through transmission. This is a pulse echo. So, through transmission. So you have, when you have a receiver and the emitter and transducers on both sides, then this is transmission. If you have it here, it's pulse echo. And why would we use pulse echo? What's the benefit of doing that? What's the advantage?
It's easier, you can just do it from one side.
Right, because you only need one-sided access, right? It's easier. It's also possible to do through transmission imaging. So I actually have done this in the lab. So you have two robots, moving together. So at GE facility, I was there a couple of weeks ago, and they have 2 big robots for big pieces of airplane. And they just move together, and they do a scanning, imaging like that, really in true transmission. So it's also possible. So here, now if you move the transducer around, at each one of these points, you are going to get some signal, right? We call this, what's the name of this signal in NDE community? What do we call this time signal? It's an A scan. It's a terminology. So if an NDE guy is talking about A scan, he's talking about a signal. Now, if you move...
So an A scan is
It's just A for letter A. There is no abbreviation.
So
it's just a signal, time signal.
So A scan is just the time signal.
That means what you are recording at one point.
Okay.
So this transducer, which you have seen in the lab, it looks like you have a lot of sensors, but I think I explained it to you that half of it, 12 work together as emitter, and the other 12 work together as receiver. It's a pulse echo transducer. You don't have 24 traces. You only get at every point one good trace, one good one. And it's a shear wave transducer. Now, it's written also here. As I said, you have the wrong copy, so all the details are written here. So 24 probes, 12 act as pulsar, 12 are receiver, and this is 55 kilohertz. So now, if you put all of these, if you are moving your sensor next to itself, then at every point you have one of these signals. If you put it all together, you get this picture here, which is a B scan. And you have seen this also in the lab when we used the big Mira system, right? So what does it show you? A B scan is an amplitude map of the subsurface. The x-axis is the distance. The y-axis is either time or thickness. It's typically time. If you know the velocity, you assume it's the same everywhere. You can't obtain it from this. Then you can turn this into thickness. But typically it is time. And then wherever you see a large, like here, a blue kind of color, that means you have reflection, right? So those are the locations when you have reflection. In this case, you have reflection from the steel reinforcement. You have reflection from the bottom of the slab, very strong. And if you look at the phase of these reflections, this I have explained to you before, we can kind of distinguish between a concrete steel interface where you have a phase shift, where at the location of the rebars, if you calculate the phase, the colors are pretty much red. It's not perfectly red because it's not completely 180 degrees. We have talked about this. And at the back wall, because it's kind of, you have air and it's perfect, you see that phase is 0. It's all green, nice and easy. So this way, we can characterize the interface. Not only say where it is, but also what type of material this is. Make sure you know how to interpret a B scan. Now, this one I have also shown you before. This kind of setup where you have, when you send from one sender and you receive everywhere else, it's called a linear array. I mean, this is the technical term. If you time your senders differently. Now everyone is sending just sequentially. There, you can apply delay to sending as you go from one element to the other. That would be called phased array. If you have ever heard like phased array, it's when you apply delay to your senders. So you apply delay so you can focus the energy at a particular point. Make sense? But this is just a linear array. We don't apply any phase difference. And what you get from it almost instantaneously, it's also a B scan in a way. Now we talk about the analysis of this kind of data a little bit later, today or on Tuesday, but for now this is a B scan. Now what are D scan and C scan? Here is me measuring manually using a very old version of this. As you can see here, this is the old version of this equipment that you have seen. Now the fancy version. So I'm measuring this point by point, 2-inch distance between each 2 points, and then you can create the map for the whole slab. Now, look at these C scan, D scan, and B scan. This is like a box that you have opened. So if you bring this all together, you are going to get a prism, right? So C scan is plan view. In NDE terminology, whenever you hear C scan, it's like horizontal cross section. That's what it is. And B scan and D scan are very similar. They are cross sections at 2 different directions. So, for example, B scan here is the smaller, and D scan is the other cross section. Make sense? So you have a 3D representation. I mean, in this case, we have an elongated, kind of like that. So wherever you cut here is B scan. If we cut here is D scan. And if we cut horizontally is C scan. That's what it is. Now, for example, here there is a delamination in core 15. You can see in C scan we see the area where it is. In D scan you see a height, and in B scan you also see the other view.
So the plan to C scan is like looking down on it?
Well, it's you are cutting at different depth, but whichever depth you want.
Oh.
But you call all of them, like you would say C scan at depth equal to so and so.
You kind of want a surface level.
Right, but ultrasound doesn't give you really anything near the surface. If you're very close to the surface, there's a blind zone. So it's not a surface measurement. In surface, you can see what's going on.
So all C scans.
It's always like it's the depth is. There is a better picture in the next picture. So it's kind of the same data after reconstruction. So it is what you are seeing here. So the cut here gives you the B scan. The D scan is this other cut. And this is the C scan. And again, you can look at the phase. This can move. So basically, you have an image of the interior. You have a complete image. You are imaging it using just moving your transducer from one point to the other, without doing any reconstruction so far. We are not talking about reconstruction. This is actually reconstructed using SAFT, but we talk about this later. You may not have any reconstruction. If you just do that, you still get a picture, right? So, this was just simple scanning. Now, tomography. Let's define a little bit the terminology here. Does anyone know what it means? Like, what is tomography? What does it mean, really? So, tomo is a Greek word for slice or section. You know how Yi was talking about his X-ray tomography experience, saying that the beam was moving around, so you get different sections, different pictures, and then through tomography you bring all this together to understand what is inside the object. So that's where this term tomography is coming from. This means slice or section. Graph, of course, is easy. We know it means draw. Now, in seismic tomography or ultrasound tomography, depending on the application, basically we want to know what is inside the material in terms of velocity or attenuation or both from measurements that you have on the surface of the material most of the time. So you have some sources, you have some receivers, and you want to know how to reconstruct the velocity or attenuation. There are two ways to do that. One is using a ray-based, which is using travel time. Or amplitude. And you use ray tracing. That means you simplify the way the energy is propagating through the medium through rays. This we did when you calculated the reflection refraction coefficient, remember? So you have this wavefront and you just show it with a ray like that. We use ray tracing, and this will be ray-based tomography. So the input to the model are travel time. So for example, you kind of look at this. Then you have the other source. And the inputs are whatever travel time and amplitude you record here, and you get, from that you want to say what would be the velocity distribution or attenuation distribution within the medium.
So you're saying that the one receiver gives you...
No, you record everything as at different receivers. You have different sources, and then you want to, from that information, at each receiver you look to see where P wave arrival is, S wave arrival is, if it's applicable Rayleigh wave arrival is, and also the amplitudes. Just like what you did in through transmission. You can extract those information from any trace, right? Now, you have to assume some sort of wave propagation. You use ray tracing, which is very simple to use. And then the art is to go from here to there. With this ray tracing and whatever you have, you want to get this distribution. This is what it is. So what other tomography we could do? If we just use travel time and amplitude, we are missing a lot of information, right? You record a whole waveform at every transducer. So it's kind of a more recent, still developing field, I would say, is the waveform tomography. So here, you don't extract travel time or amplitude, the maximum amplitude. Typically, this is what we would do. You take the whole waveform and you try to get the velocity distribution and attenuation based on that. Of course, you can imagine that waveform tomography the inversion is computationally extremely expensive. It's very hard to do, especially on a larger scale, right? But it's developing, and this is still, something like a research phase. It's not perfected yet. However, ray-based tomography is already established, especially in seismology. Not saying that it's easy in any ways. So ray-based tomography, you can use it for reflection, travel time, or amplitude. I don't write it, but it could be tomography. You know what a reflection seismic survey is, right? We already talked about that. It can be used for refraction tomography. It can be used for crosshole, or crosshole is the seismic term. In NDE, it's a transmission tomography. When I say crosshole, you know how in transmission we have receivers, and so here is sender, and here we have receivers on both sides. In seismology, since you want to probe the earth, you can't, there is like no sides to it, right? So what people do is to drill boreholes, and they lower down sources and receivers, right? I have examples from both, so you will see what I'm talking about. But in terms of concept, it's just like transmission that you have done, right? Now, if you have one source, several receivers, not only one is receiving, everyone else is also receiving. Then the other source, and so on.
And then there's like a downhole test, right?
Yes. So if you have downhole test, your source is up here, and the receivers are here.
And that's just one borehole.
Yeah. Here you don't have kind of a tomography unless you have several sources. Here you can have several sources, and then you can map the area, the velocity in the area between the sources and your receivers. I just want you to see that NDE and site characterization are very, very similar. It's just different scale. So there is always equivalent of one to the other. Now let's see how this works. So the idea is I want to show you in a, let's say, reflection time, travel time tomography, how does this actually work? What is behind this? How does the algorithm work? So here we are. The one I'm going to talk about is this algebraic tomographic reconstruction. So here is a source, and this source is, and these are the receivers. Please add that to your notes. So this is a source, this is a receiver. So there is a distance between the source and the receiver. If we consider a straight ray, it's very easy to calculate, right? And then you can, of course, move the source around. Now, at every location, you're going to get a waveform. From that, you have already learned how to estimate the first variable, for example, for p-wave, right? Thresholding, cross-correlation. Then you have a series of times and amplitudes. And then we use an iterative process to get a matrix. Each cell, we call this velocity cell. Each cell has a certain velocity and attenuation. And going from here to here is tomography. Make sense? so far? Yes, no? No questions? Now, let's see how it works. Now, imagine that I have this kind of setting. This is more seismology, but it's exactly the same in NDE. So we have a source at A and a receiver at C. And we record a time. It's just travel time. So we record a time at C. I call it time A, B, C. So how do I know what's going on? So you have to come up with a velocity model. So you kind of, from the geological information you have, if you are doing some work in seismology, or in NDT, from the information you have about your sample, you kind of suspect something is going on. You have to start with an initial velocity model. What you see here, those 9 blocks, each one is a velocity cell. So within each velocity cell, we assume that the velocity is constant, right? So it is V1, V2, V3 to V9, right? And now, once you have a velocity model, then you use ray tracing to find out how the wave is going through from A to C. You know reflection, refraction right now. So if you know, you kind of can calculate it, right? You can trace the wave. So what would be T, A, B, C? Then it's easy, right? The total time, the arrival time, it will be in each segment how much distance it's spending. So it's like D1 over V1. Write it down. You get tired if you don't write anything. So DI is the length of the ray path in the cell of velocity VI. So it would be D1 plus D2. So if we write it, we can just write it as a summation of DI over VI. I from 1 to 9. Yes.
This is just an example.
Yes. So the more cells you have, I'm just developing this. So the more cells you have, the more unknowns you have. So look at this here. What do we have? We are developing this. Good question, but this is just the beginning. So what do we have? What do we know in this equation? What do we for sure know? What do we measure? T, right? This is what we know. Do we know VIs? This is what we are looking for. So, how about DI? If we know VIs, we know DIs, right? But DI depends on VI. So this looks simple, but basically we don't know much. even for this simple 9 cell, we have 1 data, and we have at least 9 unknowns. So that's why when I said limited measurements, this is what it is. So, of course, we don't have 1 measurement. And something else before moving forward is that this ray tracing is an approximation. So there are ways, maybe you have heard of beam forming. There are ways that you can account for changes or gradients of velocity in each cell. So this ray being a straight line is only an approximation because the velocity is never constant. So it's changing within the material. So you can make this complicated by considering ray bending. There is a active research area on beam forming reconstruction. So they consider also this, the bending in the ray. This is an approximation, and even with this approximation, this is so difficult. And another thing is anisotropy. So the material normally in 3D, it's anisotropic. So it can also induce a lot more complexity to the whole issue. Otherwise, in terms of concept, you can kind of relate this 2D to 3D. Now, so you see that when we want to solve this kind of problem, we have to divide the medium. We have to have a velocity model to start with. We divide the medium into velocity cells, and you have to write down what would be the time for each ray. So go to the next slide. Now let's define here. Now we have, of course, more than 1 receiver. This is, now we have these sources and these receivers. This kind of geometry of source and receiver, we normally refer to this as common middle point, midpoint. I only CMP, this is how I know it.
Where is it located?
So you have a common middle point, and then all the sensors are on one side, typically symmetric with respect to the receivers. Not necessarily, but most of the time. It's called common midpoint. This is just the name of this arrangement of sensor receivers. If you ever heard of CMP, this is what it is. Now, if we denote Dij is the length of the ith. So here is the first subscript. The ith ray path in the jth velocity set. Right? Ti is, so we have each color represents one ray path, right? Ti is the arrival time. Time of the ith ray. So how can we relate Ti to the velocities? Try to write the formulas in a compact form. It's very similar to the previous one. So for each segment, we just divide This is the length of the ith ray path in the j velocity. So if I divide it by the velocity vj, and I sum it up over all j's from 1 to n, so n would be the number of cells, I have it. Now we can write this conveniently this way. Dij times s sub j, where s is 1 over velocity. What did we call this quantity before? Slowness, right? Thank you. This is typical. Now, tell me what's n in this little problem? 9. How many i's do we have? I's from 1 to 5. So we call this m. So we have m ray. So what we have are the ti's. What we want to know are the sj's. But remember, dij's also depend on sj's. So this is a complex problem. Mm-hmm.
So I is just the number of signals, or
I is the number of ray path.
ray paths?
So each ray is one of those colors.
Right.
Is going from one. This is what we get from ray tracing.
Why is it called M?
Just the number of them.
Okay.
Just I'm just trying to build up the matrix.
Okay.
So this is a matrix representation. We can write it like a matrix T, vector T is equal to D times S. Time vector, ray path segment matrix times a slowness vector, right? So what would be the size of each one? Write it down. Based on n and m. If you don't write, you get tired. Just put the size. You have it. No, you don't have to write it. Just put the size of each one. So for example, T is Ti. So it's like T1, T2 to Tn. So the number of rows is n. And it's a column vector, right? How about D? It's m by n. And S is n number of cells. It's a vector. That's all I wanted you to do. Okay? So, what we are looking for is S. So, one very logical way to find S is to do what? If you have this and someone tells you, okay, you have T, you want S. The first thing to do is to get S from T, you just use the inverse of D times T. But unfortunately, this never works. Why? Why can't we do that?
Because you may not symmetric.
Yeah, I mean, you can see here, even in this problem, D is not symmetric. How can I inverse a non-symmetric matrix like that? Okay, so D is not necessarily it could be symmetric when When D could be symmetric, what would be the condition? Yes, what does it mean physically?
Number of cells.
If I had 9 receivers, I had 9 traces, and the bad news is even then, I would have a problem. Can you guess why? This is a very hard guess, but try it.
We don't have inverse because we have so many zeros in it's singular.
Thank you. So for a matrix to be invertible, maybe you remember something from a long time ago, linear algebra. It has to be positive definite. Thank you. And this matrix, particular matrix, has a lot of zeros. Why Jiang thinks there are lots of zeros in this matrix? Jiang, what is your reasoning for that?
So if you divide too many cells.
No. Why you think there are so many zeros? Why a lot of Dij's are zero?
Because the idea depends on which cell you're passing through.
Yeah.
So most of the cells are not passing.
Exactly. Because every ray goes through certain cells and it doesn't go through most of the other cells. So you had a lot of zeros in this D. So it's a very nasty matrix to deal with. It's singular, and I have to tell you that the tomography, the concept is right in front of you. The art is to invert this matrix, to get these equations solved. The concept, physical concept, is very easy. You already have it. The rest is math, regularization, all sorts of singular value decomposition. Even that doesn't work. So now, if for a very simple problems, so D, let me write this down what we discussed. So D has a lot of zero elements. So it's singular. As Yi said, it's not positive definite most of the time. If the symmetry was the problem, how could we go about it? If it was only the problem with symmetry. Thank you. So if it was only the problem with symmetry, there is a trick to go around it, right? You just multiply both sides by the transpose of D. And then you would just say, okay, S is, so we inverse this one, which is 100% symmetric, always. But because of all those other issues I told you, even this matrix DTD is typically not invertible. So another, like for easy problems, another remedy is to try to write this using singular value decomposition. Have you heard about this in your life before? Yes, I'm sure. If I write it down, you remember. So singular value decomposition. So any matrix like that can be written in terms of, you can decompose it into 3 matrices. So one would be a singular matrix, and this one is called the left singular vectors matrix, and this will be the right one. So sometimes it's helpful to do the decomposition and then you inverse each one of these components to get the inverse of the of your original matrix. Have you ever seen this in your life before? The singular value decomposition. Somewhere you should have seen it, I thought. They even make you in linear algebra to do this by hand, which is pretty painful even for 3x3 to get this done. But anyway, if you in MATLAB, it's only one line. So if you don't remember, it's very easy. But again, even that most of the time doesn't work. It's not as simple to invert this matrix. There's a whole science behind it, and it's beyond us to go through all the details of that. But this is how it works. So the rest of the effort of seismologists is actually mathematics, to try to invert this. Okay, in terms of concept, we are there. Now, there is another problem. I mean, even if we could invert this, what is another? Could we just solve this directly like that? Imagine that we could invert this. We could find a way. One of these approaches I told you would work. We are lucky. And we could invert this and get S. Was it done in one shot like that? Imagine we have the T's and we find a way to invert this matrix. Either we are lucky DTD is invertible, or we use singular value decomposition, then we invert it, like that. What is the problem? Remember what I told you earlier. We actually don't know D before knowing S. That's the problem. So we have to solve this iteratively, because how do we know D if we don't know S? So you assume a model, and then you have the Dij's, then you get an S. You use this S to update D. So we call this version 1, then 2. This you compare it, you can use to get S, and so on. So it is iterative at the end. How does this iteration work? Just in a very, very simple example. Now, if we have just two medium like that, so the top medium has the slowness S1, the bottom medium has S2. Very quickly, write down the equations for T1 and T2 with the notations we had before. That means D11, D12. So it is D11, S1, D12 is medium 2, S2. That's for ray 1, which T1 is corresponding to. So I write the orange, so you see. And then we have T2. Right. So look at the A, B, C, D. Could you write them in terms of D11, 1, 1, 2? What is D21? What does it mean? It's the length. That's the ray path 2 is spending in medium 1. Just for the sake of understanding, if we look here, D21 is A plus B. And D22 is C plus D. Just that you get a visual sense of that's fine. So we have just two medium, everything is very easy. Now, it is customary to
I'm sorry, the D21 and D22, can you explain what they correspond to? So the ones that are just on the top, or
so what is Dij? Going back to the definition.
it's the
Let's read it together.
line in the I rate path and the J velocity cell.
Yeah, so it's the same definition. So D21 means
It's going to be the second rate path and the first cell. So, okay.
makes sense now?
So there's only,
So the second ray path is the blue one.
I see now.
And the second, yeah. It's exactly the reason I put this here, just, that everything kind of settles.
Okay, so we're only focusing on the second. Okay, I'm good.
Great. So now, this is just 2 medium. Remember, it's just 2 medium. So we have this, and this is the reality. This is how things are. Now, it's customary to represent these two equations in a plane, not T1, T2, but S2 versus S1. This is called, for obvious reasons, model space. We are looking for a velocity model. So it's a slowness, it's a plane where the x-axis is the slowness of the first medium, the y-axis is the slowness of the second medium. If we had 9 cells, this would be multidimensional, right? It would be in 9. We couldn't visualize it as easily. So from these two equations, we can kind of get these two equations of T1 as a function of S1 and S2 and T2 as a function of S1 and S2, this translates into 2 lines. S1 and S2 in terms of T1 and T2, right? So these are like that. So S2 equal to T1 D12 minus S1 times D11 over D12. This is the first line. It is called line T1. And then we have the other one. Right? So if we only had measurements at one receiver, we only had this one line. So any S1, S2 combination which would fall in this line would be a solution. Correct? Everyone is with me? Now we have a second reading. So the solution is where they meet, point X. Right? However, since we don't know the correct Dij's and we don't know the correct Sj's, we start somewhere here. Right? Point G. So what we get is based on some ij guess, some initial guess, times some guess on slowness, summation on J, right. Now we know what is TI observed. So we can always calculate kind of an error. Would be TI, whatever we have measured, minus what we would get from our initial model. Once we have a model, we have DII, we can calculate this and so on. And it turns out that if we start from a point like that, you can use the geometry. If we go perpendicular to this line, we can iteratively correct for the slowness in medium 1 and 2, delta S1 and delta S2. And without going to the details of geometry, you have the angles which are equal. You can just use the similar triangles. We'll see that we can have a relationship between delta Sj, which can be in this case delta S1 or delta S2, the distance to any of the lines, line I or basically line I, we can obtain it like that. So the way the iteration works is you basically start somewhere here with the initial guess, geometrically visualize, you go here, then another perpendicular, then you kind of converge to the solution. Of course, you see that even for a 2 medium, this is complicated. But this is how it's being done. If you can expand this to higher dimensions, etc., etc. Any questions so far? I'm dropping a lot of details here. Tomography by itself is a graduate class. Now, travel time tomography is not the only tomography we can do. Especially recently, people are also doing attenuation tomography. So here, this is from a different reference. So this Li, it amounts to Dij. So in travel time tomography, we try to look at the summation of Sj Dij. In attenuation tomography, this is wrong. Since when you go from one medium to the other, you have seen it even in your exam. You have to multiply the amplitudes to get the last amplitude. So instead of summation, you have multiplication of all the amplitudes, but the rest is very similar. Of course, you have the exponential term because it's not linear going from 1 to 1. But other than that, the procedure is very similar. You do all of that. Instead of working with slowness, you work with attenuation coefficient. So alpha I is attenuation coefficient, which you are all now expert to calculate. And Li is basically, we can call this J and Dij if you want to stay loyal to our previous notation. So basically in each cell, you just multiply the coefficient with the distance. And it has to be exponential. Do I need to explain why exponential? We know, right? because the amplitude always exponentially decreases over length. So that's why you have this exponential. Now, I show you two examples where people have done both, side by side. So here is an example of tomography. This is in concrete. So this is how it works. You have receivers. You can see the receivers on the back of the specimen, and you have the source on the back of the specimen, and you have the receivers on the front. Okay? So from each source, you can kind of do ray tracing to each receiver. And you have a map like that, a map of the rays that you have between different transducer pairs, source and receiver. There is something important about these maps. If you have more rays in an area, it is called ray density. If inside a volume more maps are crossing, you expect to get a higher confidence, a better confidence, a better reliable estimation of velocity in that area. So if in the middle we expect to see the best resolution in terms of velocity, because a lot of rays are passing through that region. Does this make sense? Remember how it works. You are calculating you know the time, you are calculating the arrival time, the time spent in each cell. Now, if you have a piece of material where a lot of rays are going through, this shows up in a lot of those equations, right? So the inversion is more accurate because you have more data for that particular volume. But if you have not too many rays at one corner, that area the reliability is a little bit lower. There is even a parameter called ray density, number of rays passing through a particular volume, that you can use to show as a map next to it, kind of to give an estimate of how reliable your estimations are. Not every point has the same reliability. Now, these are some typical data from this experiment. You have source, you have response. I guess by now you are all familiar with seeing things like that. You can calculate, each one of you, hopefully now, can calculate very easily the velocity and attenuation for each receiver pair. So these are the inputs to the model. And then you use inversion to get, on the right-hand side, the B is the attenuation inversion. On the left-hand side, A is the velocity or travel time inversion. I forgot to mention that they had buried a polyester plate at one corner. This is something which is used to simulate cavity or a void inside material, typically. And you can see that both tomographies basically image that part, and they argue that attenuation tomography does a better job. As you can see here, those numbers are percentage soundness. That means if it is 100%, it's the same material as the surrounding. If it is 0%, it's air. Something like that. And you have to know that, generally speaking, attenuation is more sensitive. You have read the papers, the two papers. It's more sensitive to cracks and etc. than velocity. So this is no surprise. Why won't we use attenuation then more often? Why people stick to velocity? This question I want to close the class with a discussion on that. If it is much better, as we can see and as you have read, and Why don't we use it more often? This is not about tomography. I mean, tomography is the same process, basically just here is travel time, here is attenuation. Why wouldn't we use more often attenuation? Why do we stick to velocity all the time?
Is it harder?
Why is it harder? We are getting this. Well, if you don't have any arrival, also because you have a scattering, then you also can't calculate the velocity. You have seen in your lab and in your homework that if you have also a lot of scattering, the velocity calculation is also not a piece of cake. It is hard, but it's a reason. It's not the reason. It's one reason.
For attenuation, we find the amplitude.
Mm-hmm. So what is
That it's hard to find the amplitude.
why is it hard? We are getting there.
The amplitude will be decreased after propagation.
Yeah, it will be very small, but that's good. Then we can see how small it has become.
Well, what waves is it? Is it any say that if it's the first arrival period, it's
Typically, when you calculate attenuation, you really look at the maximum amplitude. You can't really look at attenuation of each component. Let me give you the answer and let you go. The main reason is that it's very hard to quantify attenuation correctly. First of all, you have to really calibrate all your transducers in a tomography like that so that all of them are comparable. Even you saw that in your little exam problem, when you compare in contact to the sample, you have to take into account all different things inside each transducer, all the gains and so on. Another problem is any kind of coupling or pressure can change the amplitude dramatically. So let's say if you place your sensors here and you accidentally place them such that this one is more under pressure, it translates immediately into a higher amplitude on the other side. And this can produce a lot of errors. So there is a reason why people don't use it. Also, it's a better proxy for material damage, especially for distributed damage. It's really much better. Okay, we are done.